A 5.5% semi-annual pay fixed coupon bond is issued at par. That means it's issued at 100 on May 1st, 2025, matures May 1st, 2029. That is a 4-year bond. We know it's semi-annual. Our N is going to be 8. A 5 basis point increase and decrease in the yield to maturity, PV plus and PV minus, ignore those two. They are wrong. The approximate convexity is closest to. If you use these two, you would have got 1504 point something, and you knew you would have been wrong because it's a 4-year bond. So its modified duration would be 3 point something. If you square it, you're going to get nowhere near 4 digits. So we know that that's wrong. Take the 4 years and square it, you get 16. Which means your convexity should be 2 digits point something. That's an easy way to figure out if you're close or far off. It can't be 1504. I looked at it and I said, well, this doesn't make sense. Big changes like that for 5 basis point move. So let's recalculate it. 5.5%. Semi-annual. If we add 5 basis points, subtract 5 basis points, there's our yield in semi-annual. Future value of 100, payment of 275, N equals 8. There is 2.775. That's PV plus will give us 99.82283, not 98.24. And if we decrease the yield, we get 100.177, not 101.79. And then if you add the two, PV minus plus PV plus minus 2 times P naught over the change in yield squared times PV naught, you'll get 15044B. A bond pays a semi-annual fixed coupon of 4.75%. It trades at par on its coupon date of 16th December 2025 and matures on the 16th December 2023. 8-year bond. It's semi-annual. We should have 16 periods. The bond's annualized convexity statistic is closest to. Can anyone see a problem right away? Look at the cash flow, 2.35. Has a fixed annual coupon of 4.75. If we change the 5 to a 0 up here, then we'll get 2.35. I tell you, the number of mistakes is off the charts with CFAI. And we can get our convexity of cash flows by the time period multiplied by the next time period multiplied by the weight discounted by the 2.35 if we assume 4.7%, 2.35 squared. Add them all up. Since we have a semi-annual bond, you have to square the number of periods. It's 4. This is 2 to the power of 4. I should write that better rather than 24. 2 to the power of 4. You're dividing by 4. There's your convexity. For changes in yield to maturity, the convexity adjustment is most needed to account for the first order effect on bond prices. That's the linear approximation for duration. We get rid of that. Bond price risk due to small changes in yield to maturity. No, for small changes, modified duration, the linear approximation is pretty close. Nonlinear relationships of bond prices and yields to maturity is most needed to account for the nonlinear relationship. Let's see. If the yield to maturity of bond X, which is our first bond, increases by 50 basis points, that is a plus. The expected percentage price change of bond X is closest to. I'll eliminate anything that doesn't have a negative. They all have negatives, so I'm not going to get any help there. So what is our duration? What is our convexity? Let's go. Negative modified duration times the change in yield plus 1/2 times the convexity times the change in yield squared. We'll get negative 0.01791. There we are. Given a 75 basis point change in the yields to maturity for bond Y and Z, the convexity adjustment for bond Z, which is here, or bond Z, depending on what country you're in, would be greater than the convexity adjustment of bond Y, which is, there's the annualized convexity. We're talking about the convexity adjustment, which is 1/2 multiplied by the convexity multiplied by the change in yield squared. They'll both be 75 for bond Y and bond Z or Z. They'll both be 75. The 1/2 is the same. So the larger one will have the larger convexity, which is bond Z. Let's see, the convexity adjustment for bond Z would be greater than the convexity adjustment for bond Y if the yield to maturity change is positive. If it's negative, regardless of the direction. Regardless of the direction, because remember, we're squaring. So even if you have a negative change or a positive change, once you square it, you'll be left with nothing but a positive change. For a 100 basis point increase, that is an increase in the yield to maturity, and using money duration and money convexity, the estimated change in bond Y's full price is closest to. There is bond Y, there's our duration, our convexity. We want money duration and money convexity, there's our money. So it is just duration times the money. There's money duration times 0.01 because it's 100 basis points. And it's 1/2 times money convexity. With there's convexity, there's money. Multiply them. 0.01 squared. Negative 0.42742 million. This is in hundreds of thousands, so we'll just take out the decimal, put a comma there. 427,423. We have C. For a 100 basis point increase in yield to maturity, that's plus 100, and using weighted average duration and convexity, the expected percentage price change for the bond portfolio is closest to. So we're going to need weighted average duration, weighted average convexity. We have a sum total of 20 million. 5 over 20, 5 over 20, and 10 over 20 is 0.25, 0.25, and 0.5. Great. We'll just weigh the three durations, and we'll weigh the three convexities by those weights, and there are our portfolio statistics. So let's go. Negative modified duration times the change in yield, 100 basis points, plus 1/2 times the convexity times the change in yield squared. Negative 0.08948, negative 8.949%, because if you put this in percent, you move the decimal over, right? B. The bond portfolio's benchmark is a fixed income index with a duration of 9.5325 and convexity of 103.0677 based on the weighted average portfolio duration and convexity, which we calculated in the last question. We had a portfolio duration of 9.5325, portfolio convexity of 116.7493. Note, portfolio convexity matches the benchmark, portfolio duration matches the benchmark duration. Based on the weighted average portfolio duration and convexity, the portfolio should outperform its benchmark in which of the following scenarios? Greater convexity means we should perform on the way up, outperform on the way up, and outperform on the way down. Both when interest rates are rising and falling. That's what's beautiful about convexity, is you can always beat your benchmark by matching on duration and just increasing convexity. But you will learn in level 3 that everyone likes convexity, so you end up having a lower yield on those particular bonds, but a higher convexity. Get one thing, give something up. The method of using weighted average portfolio duration and convexity measures to assess price risk of a bond portfolio is best characterized as being theoretically correct. No, it is an approximation. It is not the theoretically correct way. Being commonly used by portfolio managers. Yes, because it's super easy to do. Accommodating non-parallel shifts in the yield curve. Well, whenever we're talking about duration, we're still talking about levels. We're still talking about parallel shifts in the yield curve. We can get rid of that. B.